Welcome back, students. I am Sudipto Karmakar, Assistant Professor of Physics, SVIST, and in today's video we are going to derive Wien's displacement law from Planck's law of radiation. So, what we have in Planck's law of radiation? According to Planck's law of radiation, the energy density of blackbody radiation for wavelength range lambda to lambda plus d lambda, it is equals to E lambda d lambda. It is the energy density for the wavelength range lambda to lambda plus d lambda. It is denoted by E lambda d lambda. Okay. So on the left hand side we have E lambda d lambda, which is equals to 8 pi hc by lambda to the power 5 into 1 by e to the power hc by lambda kt minus 1 into d lambda. This is the well-known expression for energy density according to Planck's law of radiation. So, if we take a look in blackbody radiation profile or blackbody radiation characteristics graph, so we can see that there is a maximum point in this graph. Okay, and from this maximum point in this graph, we have a particular value of wavelength. So, the energy density of blackbody radiation, it is maximum for a particular wavelength. And if we increase the wavelength or if we decrease the wavelength, then the maximum value also becomes very small in both of the sides of this maximum point. So thereby we can conclude that the energy density is maximum for a particular wavelength. Now on the left hand side we have the energy density, and on the right hand side on the numerator we have 8 pi hc, and in the denominator we have lambda to the power 5 e to the power hc by lambda kt minus 1. So how can one maximize the left hand side? That means how can we maximize the energy density? If we minimize the denominator, it is quite obvious. So therefore I am writing the denominator as z. So first of all we need to write one thing, that the energy density which is E lambda obviously will be maximum if the denominator of equation 1 is minimum. So if this denominator, that means this total denominator, if this denominator is minimum, then obviously on the left hand side the energy density will be maximum. Now I am writing this denominator as z. Let z equals to lambda to the power 5 into e to the power hc by lambda kt minus 1. This is our denominator. Okay. So if this denominator will be minimum, then its first order derivative will be equals to 0 from the concept of maxima and minima. So dz d lambda, it is equals to 0 for lambda equals to lambda m for a particular wavelength at which the energy density is maximum. So I am writing lambda equals to lambda m. This is true from maxima minima condition. Okay, so we have to differentiate this quantity z with respect to lambda at a particular value lambda equals to lambda. So therefore we have dz d lambda, that is we are going to differentiate lambda to the power 5 and e to the power hc by lambda kt minus 1. So therefore we have d by d lambda that is going to act on lambda to the power 5 and also that is going to act on hc by lambda kt minus 1. This will be 0 for lambda equals to lambda m. Okay, so let's perform the differentiation. So we have, first of all, we are going to differentiate lambda to the power 5 while keeping the term in the first bracket constant. That means the power will become outside and the power will be decreased by 1 unit. That means 5 minus 4, that means 4. 5 minus 1 means 4. Okay, keeping the quantity e to the power hc by lambda kt minus 1 constant. Plus, in the second term, we are going to keep lambda to the power 5 constant, and thereby we are going to operate this d by d lambda on the quantity e to the power hc by lambda kt minus 1. So d by d lambda, it is going to act on e to the power hc by lambda kt minus 1, which is equals to 0 for lambda equals to lambda m. So here I am adding the subscript lambda m. Okay. So after the differentiation is complete, so we have 5 lambda m to the power 4 e to the power hc by lambda m kt minus 1 plus lambda m to the power 5. And what about this? We all know that if we going to add derivative or differentiation on an exponential function, then after the differentiation is complete, the exponential function will remain invariant. So therefore we have e to the power hc by lambda m kt, right? Now what about the power? The quantity that is placed in the power of this exponential term also consists a lambda m term. So therefore we need to differentiate another time on this term hc by lambda m kt minus. Now what about this minus 1 quantity? Since it is a constant quantity, so therefore if we add d by d lambda m on this constant quantity, so it results nothing but 0. Third bracket is closed, and on the right hand side we have 0. Clear? So after some simplifications, we have on the next line e to the power hc by lambda m kt minus 1 plus lambda m to the power 5. Now what about this term? The first term is e to the power hc by lambda m kt. Okay, and what about this term? This term gives minus of hc by lambda m square kt, that is equals to 0. Okay, now if we rearrange them or simplify them, then we have 5 lambda m to the power 4 into e to the power hc by lambda m kt minus 5 lambda m to the power 4, that is going to multiply with this minus 1, results 5 lambda m to the power 4. Clear? Now this plus this minus results minus. Okay, so we have here we have lambda m to the power 5 and there we have lambda m square. So therefore as a result we have lambda m cube hc by kt e to the power hc by lambda m kt, that is equals to 0. So this is my equation number 3. In order to simplify this equation number 3, we are going to divide both sides by first term, that is 5 lambda m to the power 4 e to the power hc by lambda m kt. Okay, so therefore dividing equation 3 both sides by 5 lambda m to the power 4 e to the power hc by lambda m kt, we get. So if we divide equation number 3 by this particular term, then we get on the first term, if we divide 5 lambda m to the power 4 e to the power hc by lambda m kt by this same term, so we get 1. Now what about this second quantity? The second quantity is if we divide 5 lambda m to the power 4 by this quantity, then it results e to the power minus of hc by lambda m kt. Now what about the third term? In the third term is, if we divide it, then we have I guess it is hc by 5 kt, hc by 5 kt and into lambda m, which is equals to 0. Okay, so here we are taking, let x equals to, we are taking x equals to hc by lambda m kt, x equals to hc by lambda m kt. Okay, so what do we get from this expression? We have 1 minus e to the power minus hc by lambda m kt, that means minus x, minus, what about this term? This term is nothing but hc by 5 lambda m kt, so therefore we have here x by 5, that is equals to 0. So if we take this x by 5 minus x by 5 on the right hand side, so we have 1 minus e to the power minus x equals to x by 5. This is our equation number 4. Now look at this equation number 4. On the left hand side we have an exponential function, and on the right hand side we have a polynomial kind of function, that means x by 5, a linear function obviously. So on the both sides we have different functions, so in practical, analytically we cannot solve it, so we need graphical method. So it is seen that or it can be shown by graphical method, the solution of this transcendental equation, the solution for x of this equation 4. So from equation 4, the solution of x, which is equals to x equals to 4.965. It can be shown graphically. The solution for x from equation number 4, it is equals to 4.965. Okay, so this is our graphical solution for x. Now we have already let x equals to h by lambda kT. Okay, so we have already taken x equals to h by lambda kT. So from that relation we can write x equals to hc by lambda m kT, right? So if we rearrange the quantities from both sides, so we have lambda m t, that is equals to hc by x into k, right? Now what about h? H is Planck's constant. You all know the value of Planck's constant, that is 6.62 into 10 to the power minus 34 joule second, right? Now what about c? C is the velocity of light, which is equals to 3 into 10 to the power 8 meter per second. What about this x? X is the graphical solution of equation number 4. So it is nothing but 4.965. 4.965. Okay, now what about k? K is Boltzmann constant. You all know the value of Boltzmann constant is 1.38 into 10 to the power minus 23 joule per Kelvin, right? So if we put these all values in calculator, then it can be shown that its value, it is equals to 2.89 into 10 to the power minus 3. What about the unit on the left? Since all the parameters are taken in SI, so therefore the unit should also be in SI. So what is the unit of wavelength? Actually it is a length, obviously. So its unit should be meter. Now what about this T? T is the absolute temperature of the blackbody. So its unit in SI system, it should be Kelvin. So on the left hand side we have the maximum value of wavelength times the absolute temperature of blackbody, that is equals to 2.89 into 10 to the power minus 3 meter Kelvin, which is a constant. So therefore lambda m into t equals to 2.89 into 10 to the power minus 3 meter Kelvin, that is equals to constant. This is our well-known Wien's displacement law. This is our well-known Wien's displacement law or Wien's displacement formula. So therefore we have derived Wien's displacement formula or Wien's displacement law from Planck's law of radiation. Hope you will find this video useful for your examination purpose. Thank you for watching. See you in the next video. Thank you.